All right, let's get right into it. We hear all the time about the energy transition, but what does it actually take to build one of these massive utility-scale solar farms, the ones that are going to power our future? We're talking about projects that literally reshape landscapes. And in this explainer, we're going to pop the hood and see exactly how it all comes together.
I mean, just look at the scale of this thing. This is so much more than a few panels on a roof. These projects are incredible feats of modern engineering. You've got millions of photovoltaic modules, hundreds of miles of cable, and these super complex high-voltage substations, and they all have to work together like a single, perfectly synchronized power plant. The complexity is just, well, it's staggering.
And that brings up a really critical question. When you have dozens of different specialist contractors on site, one for the civil works, another for electrical, another for the transmission lines, another for the software, what is the single biggest risk? What's the one thing that can completely derail a billion-dollar project like this? It's probably not what you're thinking.
Turns out, the biggest risk isn't a faulty panel or a bad transformer. It's the problem of having too many partners, too many handoffs, and way too many gaps where things can go terribly wrong.
In the industry, they have a name for this: interface risk. Think of it like the technical and contractual gray zones between all the different teams. So, the electrical contractor finishes their job, but is it perfectly lined up for the grid team? Who's to blame when a delay over here causes a domino effect of chaos over there? This right here is the breeding ground for schedule overruns, for massive cost disputes, and, worst of all, for performance failures down the line.
So, if the problem is basically having too many cooks in the kitchen, well, the solution is actually pretty elegant and simple: a single source model. One partner who is responsible for everything. One partner with total accountability from start to finish. And this model is called EPC. It stands for Engineering, Procurement, and Construction. Now here's the key. A single EPC partner owns, engineers, and executes every single interface, from the solar panel creating that first spark of electricity all the way to the point where it connects to the grid. And those dangerous gray zones we were just talking about, with this model, they just vanish.
So let's see how this actually works in practice. We're going to start at the very beginning with the absolute foundation of any project, creating that detailed blueprint and getting a hold of every single component you're going to need.
And let me tell you, this is not just sketching on a napkin. Before a single shovel can even touch the dirt, there's a huge amount of engineering work that has to happen. This is the bedrock for the whole thing. We're talking comprehensive topographical surveys to figure out the best layout, geotechnical studies to design the foundations, and incredibly detailed electrical system modeling to make sure every single watt of power gets captured and delivered efficiently. This is the E in EPC.
Okay, once you know exactly what you need to build, you got to go out and buy it all. This is the P for procurement. And having a single EPC partner is a game changer here because they can leverage their global supply chain. They can secure everything from the best Tier 1 solar panels and trackers to those massive high-voltage power transformers and steel towers. This helps you dodge market bottlenecks and lock in all the components, which can compress your lead times by weeks, sometimes even months. All right, so the plans are done, the materials are on their way. Now we get to move from the digital world to the physical one. This is where those engineering blueprints become a reality out on the ground, through construction and, of course, the critical connection to the power grid.
The C for construction is like a carefully choreographed dance with 4 main steps. First up is mechanical. You've got to install all the trackers and mount the modules. Step 2 is electrical, laying miles and miles of DC and AC cabling. Then, Step 3 is building the substation. That's kind of the brains of the whole operation. And finally, Step 4 is putting up the overhead lines to the grid's connection point. When one partner is managing all of this, these steps just flow together seamlessly.
But you can't just flip a switch on a project this big. The commissioning phase is incredibly meticulous. First, you have cold commissioning. That's where every single connection and component is tested without power to make sure it's all safe. Then comes hot commissioning, where the system gets energized in careful stages. But the real test, the big one, is the 72-hour performance ratio test. That's what proves the plant can actually deliver the energy it's contractually promised to. Only after passing that test is it officially handed over. So we've built all the hardware, but, in the modern energy world, that's really only half the story. The physical plant needs a super sophisticated digital layer. Think of it like a nervous system to make it truly intelligent.
This diagram shows it perfectly. This is the data flow for the plant's brain, the SCADA system. It starts at layer 1, the field instruments, all the sensors out there gathering raw data.
That info flows up to the SCADA platform for analysis, and then the control engine in Layer 3 makes smart decisions. Finally, Layer 4 gives the grid operator that crucial interface, giving them total visibility and control. And the capabilities this system unlocks are just incredible. You get real-time, sub-second performance data from every single part of the plant. The system can automatically spot faults, manage alarms, and even let operators control equipment remotely. It basically turns a static pile of hardware into a living, breathing, data-driven asset.
But wait, it gets even smarter. This digital layer lets the solar farm act as a virtual power plant, or a VPP. Now, what does that mean? It means it's not just a dumb generator pushing out power. No, it can actively support the grid. It can control its power output, provide voltage support, and respond to frequency changes. It can even participate directly in energy markets, becoming a really active, valuable player on the grid. So, after walking through that entire, pretty complex process, what's the ultimate payoff? Why does this integrated, single-source EPC approach matter so much? Well, it all boils down to 3 huge advantages. First up, project velocity. By integrating all the procurement and having one single source in charge of scheduling, the entire critical path of the project gets compressed. Bottom line, you build the asset faster, and that means it starts generating revenue and clean energy way sooner. Second, grid compliance. Look, getting approval to connect the high-voltage grid is a massive regulatory hurdle. Having specialized in-house experts who know what they're doing means the designs are right the first time. There's no rework, no resubmissions, and most importantly, no costly delays just waiting around for approval.
And third, digital intelligence. The power plant is smart from the moment it's born. It's SCADA-ready and VPP-enabled from day one. This delivers immediate benefits, like data-driven operations and maintenance, and it lets the asset start participating in energy markets the second it goes online. Which brings us to a final big picture thought. As these renewable energy projects get even larger and more complex, and as the need to build them faster becomes more and more urgent, you have to wonder, is this kind of integrated, single-source model the essential key to de-risking and ultimately accelerating the entire world's energy transition?